previous lecture, I discussed how the diffraction effects limits the resolving power of optical instruments and explained the Rayleigh criterion of just resolution. Using this criterion, I derived the expression for resolving power of grating. Now, in this lecture, I am going to describe the resolving power of microscope and telescope. So, let us first discuss about the resolving power of a microscope. As we know, the primary function of a microscope is not to magnify an object, but to reveal those finer details in the object which are invisible to unaided eye. The extent to which finer details are revealed depends not on the magnifying power, but on the resolving power of the microscope. Resolving power of a microscope is conveniently expressed in terms of the smallest linear separation between two points object which are just resolved, that is, their diffraction patterns formed by the microscope objective are just distinguishable. The smaller is this distance, the greater is said to be resolving power. Let us derive this least separation between 2-point objects which are self luminous having no phase relationship. The objective of the microscope is a simple convex lens as shown in this figure, and the waves of light assumed to be of the same wavelength lambda starting from self luminous point objects O and O prime are diffracted by the circular periphery of the lens. Therefore, a diffraction pattern corresponding to each object is formed in the focal plane of the objective. Each image is therefore a diffraction pattern consisting of a central bright disk bordered by alternate concentric circular dark and bright rings. The center of the bright disk in the diffraction pattern of O is at I, while for O prime it is at I prime. If these objects are to be resolved in their images, then according to Rayleigh's criterion of resolution, the distance I prime between the center of two central maxima should be at least equal to the radius of either one. This simply means that the waves of light from O prime after diffraction by the lens should form first dark ring passing through I. This is possible only if the path difference between the extreme rays O prime Bi and O prime Ai is equal to 1.22 lambda, that is O prime Bi minus O prime Ai is equal to 1.22 lambda, where lambda is the wavelength of light waves in a medium of refractive index mu, which is supposed to be between the objects and the objective. Now, this condition we can also write O prime B plus Bi minus O prime A plus Ai equal to 1.22 lambda. If O is symmetrical with respect to A and B, then point I will also be symmetrical, that is Bi will be equal to AI. Hence, the above equation reduces to O prime B minus O prime A equal to 1.22 lambda. This equation we can also write O prime B minus OB plus OA minus O prime A equal to 1.22 lambda. The objects O and O prime are in practice so close together that we can consider O prime A essentially parallel to O A and O prime B parallel to O B as shown in this figure. Therefore, drawing the line OC perpendicular to both OB and O prime and OD perpendicular to both OA and O prime A, the above equation gives O prime C plus O prime D equal to 1.22 lambda. Therefore, we have 2 S sin alpha equal to 1.22 lambda. So, S will be equal to 1.22 lambda upon 2 sin alpha, where S is the linear distance OO prime between the point objects and alpha is the half the angle subtended at the axial point object O by the rim of the microscope objective, and lambda is the wavelength of light in vacuum. It would be observed that the entire difference in paths under consideration, that is O prime B minus O prime A, is in the medium between objects and the objective. The above equation gives the linear distance S between the just resolvable objects. The product of the index of refraction of medium in which the object is situated and the sine of half the angle of cone of rays admitted by the objective, that is mu sin alpha, is called the numerical aperture of the objective. Thus, decreasing the wavelength and increasing the numerical aperture decrease S, that is increases the resolving power of the microscope. For air, the upper limit of numerical aperture of the microscope objective is about 0.95. Therefore, with white light of effective wavelength 5600 angstrom, the least resolution distance in air is of the order of 3.6 into 10 to the power minus 5 centimeter. But by filling the space between the object and the objective by IL, the numerical aperture may be increased to 1.6. In this case, the least resolvable distance S becomes equal to 2.14 into 10 to the power minus 5 centimeter. When space between the object and objective is filled with IL, then it is called IL immersion objective. So, by using IL immersion objective, we can increase the resolving power of microscope, and by using ultraviolet light in place of visible light, resolving power can be further increased. One of the most remarkable steps in the improvement of microscopic resolution has been the development of electron microscope. From de Broglie concept, we know that electrons behave as waves when whose wavelength depends on the voltage through which they have been accelerated. If voltage varies between say 100 to 10,000 volt, wavelength will vary from 0.122 to 0.0122 nanometer. This is more than 1,000 times smaller than the visible light. It is possible to focus the electron emitted from or transmitted through the various parts of an object by magnetic lenses, and in this way details can be photographed. And in case of electron microscope, since the wavelength of electron beam is much smaller than the visible light, so we expect very high value of resolving power for electron microscope. Now, let us discuss the resolving power of a telescope. We know that the telescope is employed to view distant object, and therefore, the amount of detail which it reveals depends on the angle the two-point objects subtend at the objective rather than on the linear separation between them. The resolving power of a telescope is therefore defined as the inverse of the least angle subtended at the objective by the distant point objects, which can be just distinguished as separate in its focal planes. Let O be a monochromatic point source of light of wavelength lambda, situated at a great distance from the telescope objective AB as shown in this figure. A beam of parallel rays from this object is incident normally on the objective. The ring supporting the lens as well as lens itself serves as a circular aperture, and therefore Fraunhofer diffraction pattern is produced in the focal plane of the lens. The diffraction pattern of O consists of a central bright disk surrounded by concentric dark and bright rings, the common center being at the point P, where the point image would have occurred in the absence of diffraction phenomenon. The image of another point object O prime situated close to A is also a similar diffraction pattern with its center at the point P prime. These diffraction patterns overlap, and two-point objects can be just resolved when, according to Rayleigh's criterion, the separation P prime between the center of two central maxima is at least equal to the radius of either one. Under this condition, the angle subtended by two-point objects at the objective is taken as the measure of resolving power of the telescope. Actually, resolving power is inverse of this angle. Now, with P prime as center and radius P prime A, we draw an arc cutting P prime B at the point C as shown in the figure. This arc AC therefore represents the transmitted wave front, which gives rise to the central maximum at P prime in the diffraction pattern of O prime. The second point object near to the first, for just resolution of O and O prime, the dark ring in the diffraction pattern of O should pass through the point P prime. Therefore, AC should also be a diffraction wave front for O, so as to form in the diffraction pattern the first dark ring passing through P prime. Hence, the path difference B P prime minus A P prime between the extreme diffracted rays reaching P prime according to theory of Fraunhofer diffraction at a circular aperture should be equal to 1.22 lambda. Thus, we have B P prime minus A P prime equal to B C, which is equal to 1.22 lambda. Hence, angle BAC equal to theta will be equal to BC upon AB, which will be equal to 1.22 lambda upon capital D, where capital D is the diameter of the objective. Since rays QP prime and QP are normal to the respective wave fronts which form central maxima at P prime and P, hence angle PQ P prime will be equal to angle BAC. Here angle PQ P prime is the angle subtended at the objective by the two point objects. Hence, the minimum angular separation theta which two point object should have so that they can be just resolved is given by the relation theta equal to 1.22 lambda upon capital D. This angle is therefore the measure of angular resolving power of the telescope objective. The smaller the value of theta, the greater is said to be resolving power. Therefore, telescope with larger objective have higher resolving power. We may now calculate the value of limiting angle theta which the two distant stars should subtend on the objective of 1 inch diameter so as to be just resolved by it. Now, putting the value of lambda and capital D, we get theta equal to 5.52 seconds of arc. Thus, the limiting angle theta for 1 inch telescope is of the order of 5 seconds. Therefore, a telescope with a 200-inch objective will resolve them even if their separation be only 1/40th of a second of arc. So, it is obvious that the larger the diameter of the objective, the better will be its resolving power. Now, let us take some numerical problems. Problem number 1, find the separation of two points on the moon surface that can be resolved by the 508 centimeter telescope, assuming that this distance is determined by diffraction effects. The distance from the earth to the moon is about 3.84 into 10 to the power 5 kilometer. Now, in this problem, the diameter of the objective lens capital D is equal to 508 centimeter and the distance from the earth to the moon is 3.84 into 10 to the power 5 kilometer, which will be equal to 3.85 into 10 to the power 8 meter. Now, if r is the minimum resolvable distance between the points, then corresponding angle formed by the points at telescope objective will be equal to r into 3.85 into 10 to the power 8, and this should be equal to 1.22 lambda upon capital D. Taking lambda equal to 5500 into 10 to the power 10 meter, we have r equal to 334.31 into 10 to the power 3 meter, which will be equal to 34.31 kilometer. So, this is the minimum resolvable distance between the two points. So, now let us take another problem related to resolving power of satellites. Suppose a spice satellite circles the earth at an altitude of 150 km and is fitted with a camera having a lens diameter of 35 cm. If diffraction limits the resolution, then estimate the least separation of two small objects on the earth. Here we can take lambda is equal to 5500 angstrom. In this problem, the distance between telescope objective and object is given. Diameter of objective is also given. So, like previous problem, in this problem also we can find the separation between the two objects. So, thus we have finished the discussion related to resolving power of microscope and satellite, and we have discussed some numerical example also. Now, I will discuss some problem related to diffraction of single slit, double slit and grating. Problem number 1. Suppose parallel light of wavelength 6463 angstrom is incident normally on a slit of width 0.3850 millimeter. A lens with a focal length of 50 centimeter is located just behind the slit, bringing the diffraction pattern to the focus on a screen. What is the distance from the center of the principal maximum to the first minimum and the fifth minimum? In this problem, slit width B is equal to 0.3850 millimeter and the wavelength of light lambda is equal to 6463 angstrom. If the lens is close to slit, then the separation between the slit and the screen will be equal to focal length of the lens, that is 50 centimeter. For single slit, the condition for minima is b sin theta equal to n lambda. So, for first minimum, b sin theta will be equal to lambda. Therefore, sin theta will be equal to lambda upon b. Now, if theta is small, then sin theta will be nearly equal to tan theta. If r1 is the distance between center maximum and first minimum, then r1 will be equal to focal length into lambda upon b. Putting the value of focal length, lambda and b in this equation, we get r1 is equal to 0.8523 millimeter. For fifth minimum, this b sin theta should be equal to 5 times lambda, and by using this equation the distance between principal maximum and the fifth minimum R5 comes out to be 4.2615 millimeter. Problem number 2. Suppose plane waves of light of wavelength 4340 angstrom fall on a single slit, then pass through a lens with focal length of 85 centimeter. If the central band of the diffraction pattern on the screen has a width of 2.450 millimeter, find the width of the slit. Now in this problem, the width of the central maximum is given. This width will be twice of the distance between the principal maximum position and the first minimum position, that is 2 times R1. So here also we have to proceed like question number 1. So slit width B is equal to 2 lambda f divided by 2 R1, where f is the focal length of the lens. Substituting the value of lambda f and 2 R1, we get B is equal to 0.3011 millimeter. That is, the width of the slit is 0.3011 millimeter. Problem number 3. Suppose parallel beam of light is incident on two slit arrangement. The width of each slit is 0.140 millimeter and the distance between the centers of two slit is 0.840 millimeter. Find the missing orders and the approximate intensity of interference fringes of order 0 to 6. In this problem, slit width B is equal to 0.140 millimeter and A plus B equal to 0.840 millimeter. So we can find out N by M, which is equal to A plus B by B equal to 6. That is, N is equal to 6 times M, where M is equal to 1, 2, 3, so on. Therefore, missing order are 6, 12, 18, 24 and so on. We know that the intensity I of the double slit diffraction pattern is 4 I naught sin square beta by beta square into cos square gamma, where beta is equal to pi by lambda into B sin theta and gamma is equal to pi by lambda into A plus B sin theta. We have already discussed about these expressions while discussing the diffraction pattern of double slit. And we know that for maxima A plus B sin theta equal to m lambda, where m is equal to 0, 1, 2, 3, so on. From this equation, we can find the values of sin theta for 0, first, second, third, so on, order interference maxima. For these value of sin theta, cos square gamma will be 1. So intensity in these direction is decided by the values of 4 I naught sin square beta by beta square. So after determining the values of beta in the desired direction, we can calculate the values of 4 I naught sin square beta by beta square to get the intensity of interference maxima for m is equal to 0, 1, 2, 3, 4, 5 and 6. For m is equal to 0, I will be equal to 4 I naught. For m is equal to 1, I1 will be equal to 0.91 times I, that is intensity will be about 90% of central maxima. Similarly, I2 will be equal to 0.68 I, I3 will be equal to 0.40 I, I4 will be equal to 0.17 I5 will be equal to 0.036 I, and I6 will be 0. Thus, we see that the intensity of interference maxima is gradually decreasing as order increases. Question number 4. Light of two wavelengths 5600 angstrom and 5650 angstrom fall normally on a plane transmission grating having 2500 lines per centimeter. The emerging parallel light is focused on a flat screen by a lens of 120 centimeter focal length. Find the distance on the screen in centimeters between the two spectrum lines in the first order and in the second order. In this problem, first we have to find out the grating element A plus B, which will be equal to 1 upon 2500 centimeter, which will be equal to 4.0 into 10 to the power minus 4 centimeter. We know that angular dispersive power d theta upon d lambda is equal to n divided by A plus B cos theta. If f is the focal length of the lens, then linear dispersive power dl upon d lambda will be equal to f into n divided by A plus B cos theta. From this equation we can calculate the linear separation dl equal to f into n d lambda divided by A plus B cos theta. In the problem, d lambda is equal to 50 angstrom. So for first order diffraction we can calculate what is the value of sin theta 1, and after knowing the value of sin theta 1 we can calculate what is the cos theta 1, and then we can find out the value of dl. So in the first order, value of dl will be approximately 0.15 centimeter. Similarly, for the second order we can calculate what is the value of sin theta 2, then we can find out the corresponding value of cos theta 2, and after substituting the value in the above equation we can find the value of dl here. So dl comes out to be 0.30 centimeters. Problem number 5. A diffraction grating used at normal incidence gives a green line lambda 1 is equal to 5400 angstrom in a certain order superimposed on the violet line lambda 2 is equal to 4500 angstrom of next higher order. If the angle of diffraction is 30 degree, how many rulings are there per centimeter in the grating? So according to the problem here, A plus B sin theta will be equal to n times lambda 1, which will be equal to n plus 1 times lambda 2. Now putting the value of lambda 1 and lambda 2, we get n is equal to 3 here. Since the angle of diffraction is given, we can find A plus B equal to 3.24 into 10 to the power minus 4 centimeter. With the value of A plus B, we can find the number of lines per centimeter, which comes out to be 3086 lines per centimeter. So here we have solved some problem related to single slit, double slit and grating. Some more problems can be found in any standard textbook of optics. Thus, we have finished the discussion related to diffraction of light, and here we have mainly discussed the Fraunhofer diffraction pattern of single slit, double slit and grating. I also discuss how by using grating we can find out the wavelength of light in the laboratory, and I also discuss how this diffraction effect limits the resolving power of certain optical instruments, and I explained the Rayleigh criteria for just resolution, and by using this criteria I derived the expression for resolving power of grating, microscope and telescope. Thank you.